Welcome to Empowered Learning. In this video, we are going to talk about the concept of absolute convergence versus conditional convergence. So we've seen sometimes that it's difficult to determine whether a series converges or not. Such series are ones that contain an alternating series component to it, like this 1 raised to the n, or negative 1 raised to the n, or negative 1 raised to the n minus 1 in it. And thus, it just makes the signs of each term of the sequence for which the series is generated switch back and forth from positive to negative or vice versa. So one way that'll help us to determine convergence of a series like the ones I'm talking about here is to consider the sum of the absolute value of each term in the series. In other words, for a given series that's made up of a sequence a sub n, we consider the following series instead. Okay, so instead of just looking at what a sub n is, we just look at what the absolute value of the sequence a sub n is, basically stripping away all the negatives out of the negative terms and then just adding it up. And so we'll use this kind of series to determine whether we have absolute convergence or what we call conditional convergence. So absolute convergence happens here. A series is considered to be called absolutely convergent when the series of absolute values of the sequence here is convergent. In other words, if we go back here, if we were to add up this particular series here and it converged upon some number s, then we know that it will be convergent. And we'll call it absolute convergent. Now, the main thing here is to know that with absolute convergence, then we know that if this series is going to be convergent, then the corresponding normal series without the absolute value will also be convergent as well. So that's one of the main takeaways that we want to get out of this, and we'll probably see that as a basic fact here. Now, for conditional convergence, a series that's composed of this sequence a sub n is called conditionally convergent if it is convergent but not absolutely convergent. Okay. Now, what does that mean? So it means here that if we considered this series, if that series is divergent, but this series is convergent. Okay. And so from a simplistic standpoint, that is the difference in between absolute convergence versus conditional convergence. So absolute convergence, it doesn't matter where if your sequence has all positive values or if it alternates back and forth for these series here. You add them up, they're still going to converge upon some number. Whereas conditional convergence says that here, if we strip out the negative, the negative in all of the terms that are negative and then just add it up, that's actually going to diverge. But if we keep the negatives in for all those other terms, it will converge. Again, a good example of conditional convergence is the alternating harmonic series. Okay, and we're going to see this again. So this alternating harmonic series here is a good example of conditional convergence here. Again, if I were to do the series with the absolute value of a sub n, then we would basically be stripping out this negative 1 raised to the n here, and we would just be considering this particular series here. And of course, by definition, this is the harmonic series, which is divergent. Okay. So we know that. So that is what this situation would be here. But of course, we know by the alternating series test, and the alternating series test says that if we look at this portion of this particular sequence and the numbers that come out as a result of listing these get smaller and smaller, because of course we'll have 1, then 1/2, then 1/3, and it just keeps on going. If these numbers ultimately decrease, and in addition to that, if we take the limit as n approaches 0 of this, and of course this is definitely going to go to 0 in this instance, since these two properties are met, we know by the alternating series test that this particular series here will conditionally converge. And as I mentioned in the video that I did on the alternating series test, we know here that conditional convergence just basically means that if I took all the negative terms and I was to add them up, they would be approaching negative infinity. If I took all the positive terms of my series and I added them up, they would be approaching positive infinity. And if I was to take all the negative terms and then all the positive terms and kind of put them together, with each of them going to negative and positive infinity respectively, and the understanding here is that the size of what negative infinity and positive infinity would be like would be relatively the same, then of course this sum that we would have going on here would eventually go to 0. Okay, and so I'm going to demonstrate that explicitly here so you can kind of see what that looks like. Okay, so if we consider this alternating harmonic series again, I've listed out what the first 10 terms would look like if I was just adding up this series together here. And here, notice that I could group this as -1/1 minus 1/3 minus 1/5 minus 1/7 minus 1/9, so on and so forth. And I could take that and I can add that to all the positive terms, which is 1/2 plus 1/4 plus 1/6 plus 1/8 plus 1/10, going on, so on and so forth. Okay. So here, if we called this sum of numbers here, or we're going to say this series here, if I call this summation of b sub n minus, okay, and of course here we'll say n goes to 1 to infinity, where n is odd, then if we kept on adding up all these negative terms, we know that if we keep on adding it up, it'll be very slow, but eventually it's going to get to a negative infinity, because we know that in doing this, again, this is just a variation of the theme of the harmonic series. Is just negative instead of positive. Okay, and we can actually show that by the direct comparison test. Okay, because essentially what this would end up being is something like 1 divided by 2n plus 1. We would have something that looks like this. Or make this more correct, this should be 2n minus 1. So we have something that looks like this, and we can compare that to this series of just 1 over n. And of course, this would be the bigger series out of the two. And since this bigger series will divert, this would be the bigger series out of the two. And we would end up having to do the limit comparison test to be able to figure it out. But essentially, we'll see that this goes to negative infinity and it will diverge. Okay. And so just to be clear on this, you would consider what's inside of here to be your a sub n. You would consider 1 over n to be your b sub n, and you would be doing the limit as n approaches infinity of a sub n over b sub n. And what you're looking for is to see, is this actually going to equal to a real number or not? And if we actually took the limit of what we have there, it will end up being 1/2. And so the limit comparison test here says that since this particular number here is positive, then either both series converge or both diverge. And so since this one we know diverges, then this one is going to diverge as well. And of course, in this case, it's going to diverge to negative infinity. So that's how we know that. If we come here, what we see is that we could think of this as b sub n plus, and the sum of this would be going towards positive infinity. And of course, we could do something very similar here, where we could actually rewrite this particular series as 1 over 2n. So it'll be like this. And of course, the series that we can compare it with will again be this one. And in this case, again, this will be the bigger series. So according to the comparison test, I would not be able to use the direct comparison test, but I can use the limit comparison test, just like how I did here. And again, I would see that the limit as a sub n over b sub n as n approaches infinity would be 1/2. And since this is positive number again, tells me that either both series converge or diverge. And here, since this one diverges, then this one will diverge as well. And of course, it would just keep on going to infinity since we're talking about positive numbers. So the point that I'm making here is that this is the reason why this particular series here conditionally converges. And so what's actually going on here is that this portion of this series goes to negative infinity. This portion goes to positive infinity. And since both of these are, relatively going to the same size of infinities, if I added infinity and negative infinity are the same size, and that should be going towards 0. Okay, so that's the basic idea behind what conditional convergence actually is. All right, so again, for our recap, we know that whenever we have a series that's considered to be absolutely convergent, then we can call it absolutely convergent if we were to strip out all the negatives and the terms that are negative in this a sub n and figure out if this particular series here converges or not, and it does. Okay, conditional convergence means that this particular series with the possible negative terms in it for that sequence for every other term is going to be convergent. But when we strip those negatives out of every other term, we know that that corresponding series will not be convergent. Okay. So our first basic fact, if you're studying this in another textbook, this basic fact here, it may be called a corollary. So, but that's essentially what corollary means, is basic fact. So here we know that if a series here is absolutely convergent, then it is convergent also. Okay, so that's just, you're like, okay, well, what's absolutely convergent? Well, again, remember, absolutely convergent means that if we strip out the negatives in every other term, this new series will also be convergent. Okay, and so all we're saying here is that if we know that this series with the negatives in every other term is going to be absolutely convergent. If it's absolutely convergent, then it's going to be convergent as well. So that just basically means it's just another fancy way of saying this is going to be convergent and that series is going to be convergent as well. Okay. Basic fact number 2. And so this one says here, if we're dealing with some series that is absolutely convergent, where if we stripped out all the negative terms of the sequence that makes up the series and we added it up and it's some sum S, then any arrangement of these terms has the same sum here, okay? So in other words, if we were to list out a bunch of terms for the series and reorder in how we actually did it, and we added them up for absolutely convergent series, it doesn't matter how we do it, still going to add up to be the same thing. So this basic fact I've just stated is also known as the rearrangement theorem from absolutely convergent series. And of course, I'll go ahead and state it below here. So it says that if we have some series composed of the sequence a sub n, and it's an infinite series and it converges absolutely, and the b sub 1, b sub 2, b sub 3, all the way to b sub n, basically what we're looking at here is if we look at this a sub n as just this alternating series part here times this b sub n part, and that's what they're talking about here. So we're looking at the non-negative portion of what a sub n is. So we take this series, it converges absolutely, and we look at all the terms of this sequence that has nothing but positive terms in it. Is any arrangement of this particular sequence a sub n, then this corresponding new series with just this in it without this part converges absolutely, and we see that both this series and this series end up adding up to be the same thing. Okay, now to put that in another way, so we're considering this series here that has possible negative terms as we add it up, and we're saying that this particular series here with the a sub n, it converges absolutely. Okay, now if we are saying that this particular series with the possible negative terms in every other term in it converges absolutely, then of course by default we're also saying that this series where we've stripped out all those negatives will also be convergent. Okay, so we're also saying that. And so we know that this series with all the negatives stripped out of every other term, if it's convergent, then it should add up to be some value, and we're just going to call it S here. Now, remember that b sub n is actually understood to be absolute value of a sub n. Okay, so here we can just replace what we have here as absolute value of a sub n. Okay, and all we're saying here is that b sub n, which is absolute value of a sub n, whatever this adds up to, if it's absolutely convergent, is going to be the same thing that this adds up to. Okay, so that's pretty much all the rearrangement theorem says. Now, the important thing is that this theorem or these conditions only work for an absolutely convergent series. Okay, if you're dealing with a conditionally convergent series, we just can't rearrange things like that and make it work. Okay, so remember, with conditionally convergent series, there is a condition of the series that actually makes it convergent. Okay, and for instance, in the alternating harmonic series, it's the fact that we have the alternating sign part in it. That is what makes that special type of harmonic series convergent. If we did not have that in there, then of course all bets are off at that point, and that particular series is going to be divergent. Okay, and so this whole thing of just being able to switch around terms like how we want, it's only going to work well in being able to figure out what a series will converge to if it's absolutely convergent. And so that's one of the reasons why it's important for us to know whether we're dealing with an infinite series that is absolutely convergent or not. All right, so to summarize here, I have a few notes. This first one says, what our two definitions that we just went over and two basic facts that we also went over are trying to communicate is that if we assume that the terms of a given series were all non-negative, okay, and that's where the whole B sub n or absolute value of A sub n part comes from, and that series still converges, then the original series, just the one with the A sub n in it, with possible negative and non-negative terms that alternate sign, will also converge without question. Okay, so that's another way of just stating what I said before. Now, note number 2 says that the rearrangement theorem for absolutely convergent series does not apply to conditionally convergent series. Okay, of course, for obvious reasons, because it's for a convergent series. Okay, so in short, if we were to rearrange the terms of a conditionally convergent series with some S, then by rearranging those terms, the order in which we add things is going to sort of switch the nature of that particular series to where we may be converging upon some different number R because of that. Okay. And so that's one of the things with conditionally convergent series. We kind of got to stay in the box and keep it how it is to make it converge to this number. Okay. And if we start to switch stuff around, then the way in which that number adds and then subtracts with another number will be such that it may converge to something totally different, even though the number of terms is the same and the actual values of those terms is the same. It's the order in which you place it in that matters. With absolutely convergent series, it doesn't matter. How you switch it around is still going to add up to be the same thing. So here, as a quick example, we want to consider this alternating P series here, okay? And so, of course, this comes from the sequence 1 divided by n raised to the P. We want to know what values of P make this series absolutely convergent. Well, if it's a P series, any value of P that's greater than 1 will make it converge absolutely, which means that it doesn't matter what else we got going on in there. We know that 1 divided by n raised to the 2, or anything higher than that, we know is going to definitely converge. And of course, values of P that are in between 0 and 1, including 1, that particular P series will end up converging conditionally, okay? And so we're going to look closer at that in just a second here, okay? And so remember, we're talking about this particular series, okay? So we're not talking about this whenever this is not there, because if we did not have this alternating part here in the numerator, we just had a 1, we would have to say that this diverges, okay? But because of the fact that we have the alternating part here, that opens up the door for us to be able to say, yeah, it may not converge absolutely, but it'll converge conditionally. And again, the reason for that, if we looked at 1 divided by n raised to the P for these values here, for these values in between 0 and 1, we would have a situation here where we still have 1 divided by some number, and as P got larger, the denominator value would get larger as well. So that means that the values in this particular sequence here are ultimately decreasing. And of course, if I took the limit of this, if a value of P was in between 0 and 1, if I took the limit of it as it approaches infinity, it's still going to go to 0. So it'll meet the conditions of the alternating series test, okay? All right, so here we know that when P is equal to 1 is when the series converges absolutely. So that means that both this series, if we strip out all the negative terms in every other term, and this series, the one where we have the negatives in every other term, will both converge. Okay, so that's what it means by absolute convergence. All right, so the part B to this is, let's consider now P being 1/2. So now we're actually considering this particular series here. So basically square root of n. So we're considering this now. Okay. And so we want to say, well, why does this converge conditionally? Okay. Well, kind of what I said before. If we know that this particular series converges absolutely, then we know that if we do the absolute value of it, which is going to be this, it would converge as well. However, looking at this is a P series where P is less than or equal to 1, and we know that that particular series diverges. Okay, so here we understand that this particular series diverges where the a sub n is the one that looks like this, but here the summation of, oh, hold on, let me change this right quick. So this should be the one that actually converges, but this one would be the one that would end up diverging. Okay, so these are the conditions here for the conditional convergence, and so we're just kind of going through that right now. Whereas this one is what we're talking about here, whereas this one is what we're talking about here. And so we see that when we have the absolute value there, of course, that's going to diverge, but we know that this particular series here will converge because of the alternating series test. Okay. Now, note here that I said that we're able to say that this particular P series here diverges because of the integral test. Now, we know it's a P series, but before we could talk about a P series, we had to actually show that this particular type of series would diverge. And of course, the integral test shows us that. Okay, so if you're not familiar with that, then you want to go back and watch my video on the integral test to show you how, if we basically evaluate this improper integral, because this improper integral in concept is measuring the same thing this is. It's just that here the values of x can be numbers other than natural numbers, whereas for here in this series here, we know that the quote-unquote values of x here can just be natural numbers. So my point here is that the behavior of this series here is acting very similar to the behavior of this integral here. Okay, and so that's how we were able to show that this particular series here, when P is 1/2 or anything 1 or lower, is actually divergent. Okay, that actually comes from the integral test. Okay, so my point here again is that we know that this particular series is not going to converge absolutely because, again, we know that if I took the absolute value of this, that would be a P series that would end up diverging. But we know because of the alternating series test, those properties, this would end up converging. And of course, I go ahead and write out what that looks like here. So these two criteria. So the first here is, if we consider the non-negative portion of what a sub n is here, we see that as we list these numbers here, that the b sub n plus 1 is always going to be a number smaller than b sub n. Okay, so that's what this means. And we also see here that if I was to evaluate the limit of b sub n, it'd eventually go to 0. So these are the two properties or characteristics that we need for this particular series in order for it to be conditionally convergent by the alternating series test. Okay, so for my last example for this video, we're going to look at the alternating harmonic series 2 times the summation of -1 raised to the n plus 1 times 1 over n. And we want to show that this conditionally convergent series does not meet the criteria for the rearrangement theorem for an absolutely convergent series. Okay, so in other words, I told you that if we had a particular series that is conditionally convergent, we can't just switch around the numbers and add them up again and expect it to converge upon the same sum. And so this is an example here to sort of showcase that. So here we know that since we have this particular series is an alternating series, alternating P series where P is 1, aka alternating harmonic series, we know that this is going to be conditionally convergent. Okay, and we're just going to assume that it conditionally converges to some value L. Okay, we don't know exactly, well, we're going to act like we don't know exactly where it goes to. Okay, so we also want to note here that it's the alternating series test that allows us to be able to allow the series to be convergent, although its base is this, which is the the harmonic series, which is divergent. Okay, so here we know that because we know this particular series here is going to be conditionally convergent, it should converge upon some number. So we're just saying that it's going to converge upon a sum L. So if we do 2 times that, then this is going to be 2 times L. And that is what I am stating right here. Okay. So now what we do is just list out what this looks like. So if I actually take 2 times this alternating harmonic series and I'll list it out, it looks like this. Okay. So at this point, what I propose on doing is, let's say I want to be able to rearrange what I have here. But before I do that, I need to multiply 2 times all these terms here. Okay. So this next step is me just distributing the 2 across each term. Okay. So if I do that, and then notice how I rewrite each and every term as a fraction. Okay. And the only thing that's different now is that these first 2 terms, they're not expressed as fractions, but I force them to be expressed as fractions here. Okay. Everything else is pretty much the same. So now what I want to do is I want to rearrange the way that I add up these numbers here. And I want to rearrange it such that everything that has a denominator of 1, I add that up. Then everything that has a denominator of 2, add it up. Everything that has a denominator of 3, add it up. Denominator of 4, add it up. And so I'm doing that because I know in order to add fractions, I have to have like terms. So I kind of want to have all the things that have like terms together first. Okay. So that would make perfect sense for me to want to do that if I'm trying to figure out what this particular series is going to converge upon if I was trying to do it by brute force. Okay. So if I do that, then we see that this is what it'll end up looking like. So this is going to be terms that have a denominator of 1, term that has a denominator of 2, term that has a denominator of 3, term that has a denominator of 4, term that has a denominator of 5, so on and so forth. Okay. And when I go and add up all these, then I see I end up having this here. But notice that when I figure out, well, what is that? When I write it back in this summation notation, notice that this is just the summation of -1 raised to the n plus 1 times 1 over n. And I'm saying that this equals to L. Well, I have a problem And that problem is we said that something else that was different equals L, okay? Because you remember back here, we just said that 2 times all this business here was equal to 2L, right? So we just said that, okay? So here, if it's 2 times all this, then all this should just be equal to 2 times that. But we see that it didn't come out to be that. What it actually came out to be is just L. And how do we know it just came out to be L? Because when we come back up here, remember that we said up here that if we didn't have this 2 here, we wouldn't have this 2 there. And we see that the summation of -1 raised to n plus 1 times 1 over n, that would just equal L. Well, again, what we're saying here is that 2 times this and 1 times that could equal to the same value, okay? Now, again, we're assuming that we don't know what L is. So we have to treat it as if it's a number that is not 0, because the only way that 2L and L would actually end up being the same thing is if L is either converging to 0, and that's pretty much it, okay? So here, again, we're saying that this series, which is this one multiplied by 2, actually ends up being the same thing here. But of course, if L is supposed to be any real number, I can't say that 2 times some real number is going to be equal to that real number, okay? I can't say that in general. The only way that this is going to be true is if L is equal to 0. And again, I don't necessarily know that because we assumed that that wasn't going to be the case, okay? So here we have a contradiction. And so the thing is yes, this time we're dealing with the alternating series, and yeah, we kind of assume that, all right, well, that particular series would end up converging to 0. But what if we had something different? Okay, if we had something different than that, then this same result would end up happening, and we still have the 2L equals L, and it wouldn't make sense because we know if L wasn't 0, then these two things wouldn't be equal, okay? So again, this is an example of what it looks like in general, using a very simple alternating series to show you why the rearrangement theorem does not work for conditionally convergent type of series, okay? And so with that, this concludes this video on talking about the difference in between absolute convergence versus conditional convergence. And of course, I also threw in here an example of how the rearrangement theorem for absolutely convergent series would not work with a conditionally convergent series. So if you're watching these videos in order, the next video you should watch should be the ratio and root test video, because this one, the ratio and root test, will talk about simple tests that we can do with some series that look certain ways to be able to test for absolute convergence or not. And I'll see you in that video. Take care.